Okay, it's Wednesday here, Physics 1151, 102. We have a short lecture today. We're going to finish chapter 25 tomorrow. Today we're just going to talk about the electric potential or the voltage and its relationship to uniform electric fields. So we'll start off with an application of a uniform electric field, the parallel plate capacitor once again. Then we'll go into equipotentials and the relationship for the electric field direction. Homework 7, I'm going to upload it Saturday, probably late morning, and it will be due Friday night, the 19th at 11:59 p.m. And we'll have our second quiz on Monday concerning homework 6, whose solutions have already been posted a few days ago to the As You Learn homepage. So let's go back to the parallel plate capacitor. We're going to be visiting this quite a bit. And recall that the change in the difference in potential energy is equal to the negative of the work done by the electric field in moving a charge from point A to point B, or some distance dr. And if the field is constant so that we don't need to integrate, then the force is just QE. So in this case, we have a uniform field. And what we want to know is how much work is done by the electric field in moving this positive charge from plate A, which is the negative plate, over to plate B. So for example, this could be a battery. This is the electric field going from the positive to the negative terminal, and we maintain a voltage by chemical reactions which push positive charge over to the positive plates and negative charge to the negative plate. So let's calculate the work done by the electric field. Okay, if the force is constant so that we don't need to integrate, and if the distance d is the distance at which the charge is moved, then the force is equal to the electrical force, which is QE, and that's pointing down, times the displacement d, so it's moving a distance d, times the cosine of the angle between the electric field and the displacement. And so in this case, the electric field and the displacement are anti-parallel, so the angle between them is 180 degrees. Cosine of 180 is -1, and the electric field does work negative Q times ED in moving the charge from A to B, or from the negative to positive plate. And since the electric field does negative work, there's positive work done against the field to move it from negative to positive. And with a battery, that positive work would be done by a chemical reaction. Chemical energy is used to move the positive charges over to the positive plate. They're repelled by all these other positive charges, so there needs to be work done against the field. Now, once we get the work done by the electric field for any problem, we can get the change in the electric potential energy, which is just the negative of that. It's the negative work done by the field. And so the change in potential energy for this positive charge Q is just Q times ED. Okay, so that increase in potential energy for the positive charge and going from A to B. Okay, that's just because we're pushing it uphill. Now, once we get the change in electric potential energy, we can divide by the magnitude of the charge Q, and we can get the potential difference delta V. So that's QED divided by Q is ED. In other words, the potential difference between the two plates is just the electric field strength times the separation. Probably the easiest formula you'll remember in physics is just delta E is equal to Ed, okay? And everybody has to have a friend or a relative named Ed. So this is an easy one. Okay, the potential difference is equal to E, electric field strength, times D. And this gives us an interesting relationship because if we can measure the potential difference between 2 points and we know the spacing, we can calculate the electric field, and the electric field strength is just delta V over D. And since delta V has units of volts and D has units of meter, the electric field also has units of volts per meter. Okay, and so now we have two different definitions. The electric field is equal to the force per unit charge exerted on a charge Q. The electric field strength is also related to the difference in potential per unit meter. In other words, how fast the potential is changing with space. In this relationship, the second one is especially useful in practice. So in other words, potential differences are measured very easily using a voltmeter. Okay? In other words, we can take a meter and measure potential differences between any 2 points in space. Okay? And if we know the potential difference by measuring with the voltmeter, and if we know the distance between the 2 points, we can get the electric field strength as the gradient. Okay, in other words, how much does the voltage change per every 1 meter? And that's the electric field strength. And so in practice, this is the way that the electric field strength is typically calculated. It's calculated by mapping out the voltage using a meter or some other device, and you can get from the gradient, we can get the electric field strength. And we'll be doing that more in the next chapter. But this is a very important equation here. Potential difference is ED, E-D. So what does this say here? Okay, if the potential difference between 2 plates, delta V, so here's a negative plate and a positive plate. And let's suppose that the positive plate is at a potential that's 1.5 volts higher than the negative plate. So for example, a AA battery, okay, has about 1.5 volts. Okay, what this says is that the potential difference between the plates depends linearly on the distance d between the plates. And so that means that the potential becomes progressively smaller as we go from the positive to the negative. In other words, it decreases linearly with d, or it increases linearly with d if we're going from the negative plate to the positive plate. Okay, and so what we can do here is we can draw these surfaces called equipotentials. And equipotentials are a lot like contour maps of constant elevation on geographic maps. Only these are surfaces of constant voltage, constant potential. Okay, and so if the negative plate of the battery is at 0 volts and the positive plate is at 1.5 volts, well, then about 1/3 of the way between the plates, we know the voltage is going to be 1/3 of the way from 0 to 1.5, which is 0.5 volt. And 2/3 of the way from the negative plate to the positive plate, the voltage is going to be 2/3 of the way from 0 to 1.5. And so everywhere at that distance is going to have the same voltage. And so these equipotential surfaces are planes of constant voltage. And so we can draw these equipotentials if we're able to measure the voltage everywhere. But for this case, the voltage increases linearly as we go from the negative plate toward the positive plate. So the other thing we notice here, so here's an example of a couple plates here. This one, they all have 100-volt potential difference between them, okay? So in this plate right here, the positive plate is 100 volts more positive than the negative, and we can call the negative 0, and then the positive would be 100, right? And then a quarter of the way between the plates, the potential would be 75 volts everywhere. Halfway between the plates, the potential would be 50 volts. 3/4 of the way to the negative plate, it would be 25 volts, and then down to 0 here. Okay, and we could also call the positive plate 0 and the negative plate negative 100 volts, since all that matters is that the difference is 100 volts between the two. And in this case, then the equipotentials would be negative 25, negative 50, negative 75, and negative 100. Now, there's nothing sacred about these numbers. I could have drawn 10 equipotential lines and have them change by 10 volts each one, going from 100 to 0. But the main point here is that the voltage decreases linearly, going positive to negative. And so these equipotentials change at a constant rate. So the other thing here is that the electric field we know in a parallel plate capacitor points from the positive plate toward the negative plate, positive terminal to the negative. And if you look here, what we see is that the electric field direction is perpendicular to these equipotential surfaces. The equipotentials go up and down. The electric field points from left to right. And although we're drawing this for a parallel plate capacitor, this holds for in all cases, okay? So in other words, if we find these equipotential surfaces, the location of all the points of constant voltage, the electric field direction will always be perpendicular to these equipotential surfaces, and it will always point from more positive toward more negative potential. Okay, so this applies all the time. We just showed it here for the case of a parallel plate capacitor. So just to kind of summarize this, the magnitude of the electric field strength at any location is equal to the rate at which the potential V is changing. In other words, the potential difference in volts per meter. So, for example, if the potential difference between 1 millimeter, suppose D is 1 millimeter thickness here, 1 millimeter gap, and the voltage difference is 100 volts, then the electric field is delta V over D is 100 volts divided by 1 millimeter is 100 volts per millimeter, or 100,000 volts per meter. So that's the electric field strength between the plates if this was a 1 millimeter spacing between the plates, and we charge these up so that the positive plate was 100 volts more positive than the negative plate. So commit this formula to memory here, this relating the potential difference between 2 points to the electric field strength and the spacing. So the other important point that we discussed again is that the direction of E at any point in space is perpendicular to the equipotential surfaces, and it will point from higher V to lower V. And this can be verified if you stick a positive test charge in the field lines will go away from positive and toward negative, and this because the potential energy of the positive charge increases when it goes opposite of the field. So the electric field always points in the direction of decreasing voltage, and it's perpendicular to the equipotentials. So here's an example, an important example if you have a conductor. Okay, so suppose you put some charge on a conductor, like a metal, and suppose we put a bunch of positive charge here on the surface. This charge will spread out because these positive charges want to get as far away from possible to each other. They want to minimize the repulsions. So the charge will spread out over the metal, And since no work is done in doing this, then the potential difference along the surface of the metal is zero. In other words, if I have a metal, the potential on any point on the metal surface is the same. So a metal is an equipotential. The potential is constant everywhere on the metal surface. Okay? So why is that? Well, okay, suppose it wasn't. Suppose that the potential was more positive to the left over here than it is to the right. Well, that means that there would be an electric field pointing from left to right, and the electric field would exert a force on the positive charges until they moved from left to right and the field vanished. So in other words, the potential along the surface of any metal is a constant, okay? And what we didn't prove here, but we will in the next chapter most likely, is that the electric field is always zero inside a conductor. And this is kind of nice because if you have sensitive electronics inside a metal case, this metal will shield the electronics from stray electric fields, which could cause noise or damage to the electronics. So we can place these electronics inside a metal box, and we know that the electric field inside the metal will be zero, and so the metal will shield the electronics. Now, since the electric field is always perpendicular to this equipotential, and since the potential is constant along the surface of a metal, that means that any electric field outside of the metal has to be perpendicular to the surface. It has to, because it's perpendicular to the lines of constant potential. So with any metal, in summary, the potential is constant along any surface because the charges will spread out to minimize the repulsion. It can also be shown, we're not going to get into it, is that the electric field strength and the charge density are the largest at all points of a conductor that are the sharpest curvature. So in other words, at the sharpest points of the metal, the electric field strength is going to be strongest. And in fact, this forms the basis for spark plugs, okay? The field will be strongest at the tip because there's the greatest curvature in the metal surface, okay? So that gives rise to the largest field at the tip of the plug. So let's do an example here. Suppose that we have a 12-volt battery, meaning that the positive terminal is 12 volts more positive potential than the negative terminal. So this is a car battery, is 12 volts, one example. And suppose that this battery charges up a capacitor. So it puts equal amounts of positive and negative charge on these two parallel plates, okay? And suppose that the plates are separated by 1 millimeter and the electric field is uniform. So calculate first how much potential energy a proton loses as it goes from the positive plate toward the negative plate. So let's do that one first. So what we know is that the proton, if we know the charge of the proton Q, it's the same magnitude as an electron, 1.6 times 10 to the negative 19 coulombs. And we know the potential difference, which is the change in potential energy per unit charge. Then we know that the change in the electrical potential energy is Q delta V. And so we multiply the charge by delta V, and we get the decrease in the potential energy. Now notice here that the change in the potential is negative. Why is that? Well, it's because we're going from the positive plate of the battery to the negative plate, okay? And so the change in the potential delta V is negative 12 volts if you're going from positive to negative. It would be plus 12 volts if you're going from the negative plate toward the positive plate because you're increasing your potential. So in other words, in this case, the proton is losing potential energy. Okay. Now in part B, let's calculate the magnitude of the electric field. Okay, well, remember delta V is ED, and we know delta V is 12 volts, and we know that D is 1 millimeter. So that means that the electric field strength is 12 volts divided by 1 millimeter is 12,000 volts per meter. Okay. In other words, for every 1 meter in the electric field strength, the voltage would change by 12,000 volts. Okay. So now suppose you have this 12-volt battery and we want to make the field 10 times bigger. Okay. How can we do it? Okay. Well, let's go back to delta V as ED. Okay. In this case, delta V is fixed because we have a 12-volt battery, but we can make the field strength larger by decreasing the separation between the plates. So if we make the plate spacing 10 times smaller, in other words, push the plates in so they're only 0.1 millimeters, we will make the electric field 10 times larger, or 120,000 volts per meter. And it turns out that to cause a spark in air, it's somewhere on the order, if I remember correctly, I've got to remember this, I'll get back to it next time, but it's like 300,000 volts per meter, or 3 million, it's one of the two, I'll look at it, is the change is the potential difference per meter, and that's a strong enough electric field to cause a spark to ionize air. I'll get you the number next time. So final example here is rank in order from largest to smallest the potentials between the two plates of the capacitor, okay, A, B, C, D, and E. Okay. Well, we know that the potential at the positive plate is the largest, the potential at the negative plate is the smallest, or this is the most positive, this is the least positive, and we know that the potential decreases linearly as we go from the positive plate to the negative plate. Okay. Now A and B are the same distance from the positive plate, and so they must be at the same potential, and they must be higher than the other points because they're the closest to the positive plate. So VA and VB are equal and are the highest. Okay. VC is higher than D and E because it's closer to the positive plate, but it's not as positive as A and B. And so VC is the third highest. And then points D and E are they're equipotentials. They're at the same distance from the positive plate, and they're the most negative or the least positive. And so the voltage decreases linearly again as you go from the positive plate toward the negative plate. Now, voltage is the potential energy per unit charge, okay? And if you recall from fluids, pressure is the potential energy for unit volume, okay? And so it turns out that voltage plays the same role in moving charges as pressure does in moving a fluid. Okay, so we can draw the analogy with voltage is like pressure. It behaves the same way. A battery is like a pump. So what does a pump do? A pump takes fluid and it moves the fluid against the gradient, right? It moves it uphill from low pressure to high pressure. It pumps against the gradient. Battery does the same thing. A battery takes positive charge and it pumps it up from lower voltage or lower potential toward a higher potential. It pumps against the gradient, so it pumps it uphill. And so we'll see in circuits that batteries behave with electrical circuits a lot like pumps behave in water circuits, pipes. And so pumps create a difference in pressure, batteries create a difference in voltage. And so we'll get back to this more when we get to electronics. So I said today would be a little bit short. So we'll finish up on chapter 25 tomorrow. We'll be doing potential due to point charges, and that will finish off 25 then. And just a reminder, I will assign homework 7 on Saturday morning, and it'll be due the following Friday. So have a good day.